Okay, so hello and thank you all for being here today at our postgraduate course in Artificial Intelligence with Deep Learning final project presentation. We are so happy to be here today with all of you to present our project, Device Control with Gestures, we have been working on during the last 3 months. Let me present our team. We are Enrique Gonzalez, Gerard Pons, Sofia Limon, and myself, Celia Santos. And our project advisor has been Amanda Duarte, PhD candidate at the Barcelona Supercomputing Center and UPC. Let's put you all in context of how the flow of this presentation will be. In the first place, we'll explain the motivation that has led us to this project. Then we will explain what dataset we have used and the model we have obtained, followed by the step-by-step process we have taken to reach out the final solution. Next, we will show you our end-to-end system, which integrates all the parts developed during the project that allows like the real interaction between the neural network and the device control with the gestures. Afterwards, we will do a little recap on the main goals we set at the beginning of the project, how far we have arrived, and the work pipeline with the Gantt chart. To finish the presentation, we emphasize on the conclusions and next steps. So how many times have you been watching TV and couldn't find the remote? Or you are cooking, eating, and your hands are too messy to interact with the device? Or maybe you would simply like to use devices more intuitively. We use gestures every day of our lives as our primary way of interacting with other humans. So our project emerges as a way to interact with devices in an easier, more convenient manner. We have created a gesture recognition system that works by capturing videos with the camera to perform basic tasks on a personal device. But our idea is that it can be further developed to different environments, like for virtual assistants or home appliances, or in a car instead of taking your eyes off the road, or in a medical environment, for instance, for a doctor to explore radiology in the middle of a surgery. So, as our data set, we have chosen the gesture data set, which is free of charge for academic research, which is a large collection of labeled video clips that show humans performing predefined hand gestures in front of a laptop camera. The original dataset is composed by 118,000 videos in the training set and has a total of 27 labeled classes. In order to reduce the amount of resources and reduce the complexity of the training, our task has been to select a subset of only 9 of the 27 original classes, which is equivalent to 42,000 videos of training set. As it can be seen, we have selected 7 useful classes. That means only 7 classes of the 9 actually performs gestures. And then we have a no gesture class and doing other things one. So that's a total of 9. So let's take a look to our model's final solution before explaining how we got here. Remember that the goal of our project is to map videos of people making hand gestures to one of our 9 classes. Thus, the input of our network are RGB videos. So first of all, when an RGB video is received, its optical flow is computed, and then we extract features from both the optical flow and the RGB videos using an i3D pre-trained network. Afterwards, these features are joined and fed into the network, whose outputs are the probabilities of each class.
Okay, so this project evolution section explains our journey to obtain the final model. We will start explaining how we use transfer learning and feature extraction. And afterwards, we will see the evolution of the model approaches from a single RGB stream to two streams, merging RGB and optical flow. And finally, how we did the hyperparameter tuning and further exploration of data augmentation.
Enrique? I think he lost the connection. Well, I can continue if not. Well, since we didn't find any pre-trained model on gestures data for extracting features, which is a model pre-trained on the kinetics data set, which is a large action recognition data set, including human-to-human interactions.
Sorry.
Okay, Enrique, if you want.
Yeah.
I can explain that
okay.
That one, and then you continue. So, well, regarding the network, we selected an inflated 3D convolutional net with ResNet 15, which is a pre-trained intern on ImageNet, since it's a state-of-the-art model with a good balance between accuracy and computational requirements. We use it in our model to extract the representations from our data to determine the right gestures by training a 9-level labels classifier.
Okay, sorry for the connection outage. Let's talk about feature extraction now. In order to train the gesture classifier, first of all, some pre-processing has to be done to fit all the videos of our dataset through the feature extractor and getting the features. This was done by means of 3 scripts. The first one converts each sequence of frames into a video by using OpenCV library. The second one is the script from Gluon that extracts the features for each video that are a tensor of 1 per 2048 dimensions. And the last one joins all the features into one single pixel file to facilitate loading the dataset into the gesture classifier.
Okay, so first, as a first approach to our problem, we did, well, what we thought the logical thing was putting the plain RGB videos for through the feature extractor. We then designed a classifier network on top of it, consisting of connected layers, relay activations, and dropout layers to address the considerable overfitting that we were encountering. Then, after some training and hyperparameter tuning, we obtained an accuracy that was about 70%, but it was still far from what we wanted to achieve. So to try to understand where the model was struggling, we computed the confusion matrix, which is the image on the right. So to break it down, on the vertical axis is the ground truth label, and along the horizontal axis, the prediction of the model, sorry. So you can see here that there's some interesting results. The model is particularly troublesome around 4 labels. So swiping up, swiping down, swiping left, swiping right. And we believe it was because it's the same sort of movement, but in a different direction. So here comes in our second approach. We concluded that we had to capture better temporal and directional information. And so that's why we chose to include optical flow of the videos. If you look at the video clip, on the left is the original video, and on the right is the optical flow. So basically what optical flow is the apparent movement of objects within a video. So with these new optical flow videos, we extracted the features from them in the same way as we did with the RGB videos. And after training the model, again, in the same way as our first approach, we observed that we had an accuracy of about 57%, mainly because the model couldn't detect videos with little movement. For example, we have a stop sign or a thumbs up. So these gestures weren't classified very well, but you can see in the confusion matrix that the troublesome gestures was reduced, like swiping left and swiping right. So this confirmed our hypothesis that a better directional information was captured. So although the results were satisfying, we thought they could be better. So that's why, after analyzing several of the videos of Optical Flow, we saw that there was a lot of background noise in many of the videos. So we tried with some pre-processing. So initially, we tried with image quantization and noise reduction, because we thought by reducing the colors in the image, there will be less variation within the image, and it might improve the optical flow. But the results were pretty bad. You can see that the variation within one single frame is much better, but the variation within consecutive frames was still far from good. And the second approach was reducing the brightness of the image and calculating the flow on top of that. So as you can see from the right image, the moving background, which was our initial problem, it became static. You can't really tell from the image, but yeah. The background became static, and the hand gesture was the only real movement in the image. But we couldn't get this to work for consistently throughout all the videos. And as a third approach, we tried sparse optical flow. It's a vector representation, but we thought because we only need movement, we only need the direction of the movement, we thought maybe it could work better than dense optical flow. However, using the same parameters in one video and another video, we obtained very different results. So it worked well in some videos and it worked very bad in other videos, as you can see. So unfortunately, after several experiments, we couldn't find how to improve the optical flow. So we decided to move on with the original one and continue advancing with the project.
For the first and second approaches, we decided to use a model with two streams, following the ideas of the Quo Vadis actor recognition paper. We use one stream for RGB videos, the spatial stream, to help with the general classification task, and another one for the optical flow videos, the temporal stream, to address the confusion of the troublesome gestures, and combine both streams in order to get the best of both models. To join the features, we explored different possibilities following the bilateral publication that deal with spatiotemporal streams of low-resolution videos. That was exactly what we were working with. We tried adding I3D features, concatenating them, and retaining the maximum value of the 2048 features with work with one neural network, and also using two neural networks and adding up the logits. We tested different methods with the similar standard networks in order to get a standard point, and we get the following results that showed that the different methods have a very similar performance. Only we can find that maybe the logit addition and the feature concatenation were standing out from the rest. So we have to decide which one of them to choose, and we tried to discriminate by the number of parameters to try to minimize the computational time and cost, and for the number of hyperparameters in order to address the tunability of the model. Regarding the number of total parameters, the difference between the models was roughly 3 times less in order of magnitude of the total number of parameters, so we consider that to be negligible. And tunability, the hyperparameter tuning, we found out that the logit addition had the double of the hyperparameters to tune. So we went with that in order to have more room to play with. And we finally choose the logit addition method. And we can see an overview of the architecture of it on the right that will go on top of the inflated 3D network that we used previously to obtain the features. As we can see on the results of the figures, with the approach, the accuracy went up to 80%, and we reduced the number of confusions of the troublesome gestures by half, backing up our initial hypothesis. And with this approach, however, we have double of the data, but we thought that this 10% increase was worth it, and we kept with that to further explore it.
So we do some hyperparameter tuning. For doing that, we made use of RayTune library with the purpose of minimizing loss for the one-stream model of the classifier. We check the following parameters that are learning rate, batch size, and hidden layer size, whose tested value ranges are shown in the table on the left. All trials were done in series of 50 executions of 20 epochs each, and with a dropout of 0.5. To do the first sequence of trials, we selected the HI scheduler, that is an evolution of hyperband. We obtained it this way a set of parameters that minimize loss that we call best params so far. The next trial sequence was done changing the default RayTune search algorithm, that is random and grid search, by hyper optimization search, that is supposed to perform a more efficient hyperparameter selection than the previous one. A summary of the best results is shown in the table on the right, where you can see that the previous so-called best parameters that were obtained by using the default search algorithm are the red ones, and were used as input parameterization for hyper-optimization search. And its execution was done in first place by the algorithm. And after that, they made the rest of the trials. Here we can see a summary of 8 trials, and the best ones are that are painted in green color. But however, we got only a marginal improvement of 2% compared to the default values that we obtained with the default search algorithm. So after doing hyperparameter tuning and getting the best accuracy so far, and having already explored optical flow improvements, we still wanted to try a last attempt to make our overall accuracy better. So we performed an augmentation of the training dataset by means of a new script, that is the yellow box in the pictures, to make some transformation to the frames. A scheme of the complete procedure can be seen in the picture. It must be noted that this is a very time-consuming process for doing all this procedure to calculate the augmented data. In addition, it was somehow complicated to find out which transformation could we apply, because some of them couldn't just be made as adding blur or noise to the pictures that would ruin optical flow, because they created artificial movement, or also flips that would have changed some of our video labels. So we ran a total of 3 trials, combining some non-so-dangerous transformations as zoom, some color characteristics, and translation. Unfortunately, none of them allowed us to improve the previous results. Possible reasons could be that the classifier was already fitted for our task, but that we just didn't find the right transformations to apply to the pictures.
Well, now that we have seen how to create our model from scratch, Let's see how the network has been embedded within our end-to-end system, which allows the user to perform actions on their computers using gesture control in real time. We developed 2 different applications for that that work together using the client-server paradigm. In this way, the tasks are shared between the server and the client. And that last one makes requests to the server and waits for its responses to decide what action to take. Thus, the way the whole system works is as follows. The videos are captured in a local computer, sent to the cloud where they are processed and classified, and then a response is returned, and our computer performs the action contained in our reply message. Then to message the messages sent between the server and the client, we use remote procedure calls, which is a protocol that a computer uses to execute code on another remote machine without having to worry about the communications between them. So, well, this is handled by the open source IMQP message broker, RabbitMQ. So we tested our system deploying the server and the broker on Google Cloud Platform, and then the client application running on our local machines. And here we have a demonstration on how it worked. At the bottom of the screen, we have a cheat sheet explaining what actions performs each gesture. So when the application starts, a new window is opened, and each action we perform will be done on that folder as a root directory to record videos that are sent to the processing engine in the cloud. We can see that each response we get from the network is shown like here in the upper part of the video. So when we slide the fingers up, we create a directory. And if we thumb up, we create a file inside of it. So if we stop, we close the opened file. Then by sweeping right, we move forward in a directory. As there is no one, it shows a pop-up. And we can close it by turning hand clockwise. Then we can move back in the directory by sweeping left. And we can remove everything in that directory by sliding 2 fingers down.
These are the milestones proposed on the mid-project review. The first 2 ones that involve finding and preparing the dataset, setting up the virtual environments, and the extraction pipeline were already accomplished by then. And we were in the middle of the 3rd one, and the only part left was training and tuning the already designed model. Then the more technical milestones were achieved that require capturing and treating the videos appropriately to be fed into a neural network and mapping the output of the neural network to specific Linux commands. And those were also achieved on time. To the general planning of the presentation, this is presented in form of a Gantt chart. We approach the first part like a research task in where we look at what had been done, what could we do, which if our ideas were feasible with the resources available online. Once we done that investigation part, we started the development one, in which we design, train, and hyperparameter tune our model. While working on the hyperparameter part, it was a more static and extensive task, requiring more computer hours than our hours. Part of the team worked on the technical implementation. And so when that was all done all together, after we finished with the hyperparameter tuning, we continued with deep learning stuff, trying to improve the data, the model. We tried data augmentation and optical flow enhancement. we spent a lot of more time in that part than the one that was previously planned, because we received that feedback on the midterm presentation, and it proved to be a very good suggestion as we dug deeper into neural networks and learned a lot of additional concepts. And once we had all the two parts together, we joined them, we tested, we made final minor changes, and we just prepared the delivery and the presentation.
And to conclude, well, we've learned that if anyone wants to start a project with good results and low resources, well, transfer learning is a good solution. We calculated that one single forward pass through the feature extractor network took about 7 hours, so training a model from scratch would have been very computationally expensive. As for becoming cloud compute masters, well, that came after several drawbacks, one of which was deleting the instance in the middle of the project, and we had to start all over again from scratch. And then the other one was well, the adventure of trying to assign a GPU to Google Cloud Compute, which took us like a week to figure out. But yeah, in the end, we became confident using the environment. And finally, having completed this prototype as a first step, we know that our initial proposal of building an intelligent application with gesture recognition is not far from achievable. Yeah, thank you very much.